Hi, welcome to Broke Abhiyantrics. So today again we are going to take up the concepts of strength of materials, and we are going to talk about the first question here. Right, so this is a question on fatigue. A fatigue crack in a sound and smooth specimen takes. Right, so before talking about this particular question, let me just list out the different factors which affect the fatigue life of the material. Right, so I'll just list it down. Please bear with me for a minute. So first one is going to be the stress concentration. Right, so this stress concentration, if there is any increase in stress concentration of a particular material, let's say if I have a material here and I have a notch here, so we are going to have stress concentration here, the crack is going to form here. Right, so these are some of the different factors which is going to affect the fatigue life, meaning if there is a notch or a keyway, or let's say uh, a sharp change in any cross-sectional area, the fatigue life is going to decrease. Right, so that is the first one. The second one, we are going to have something called as surface roughness, meaning, so if a surface is smooth, meaning that the fatigue life is going to be more. Right, so we can use that particular material for a long, or a particular element for a longer duration of time. Right, so and then the next one is we have surface condition. Right, so meaning if a material has been surface hardened, let's say for some process like nitriding, or let's say carburizing, etc. Right, so if we do all of these kind of surface treatment for a particular material, its fatigue life is also going to increase, meaning that we can use that particular material for longer duration of time. And next, finally, the last one is the environment, meaning how good the surface environment is, meaning that if the material is experiencing corrosion. Right, so if the particular material is undergoing some corrosion, if there is a corrosion on a surface, this corrosion is going to enhance the uh, initiation time, meaning that the initiation time for a particular material, if there's a corrosion, is going to be less. The initiation is going to be very less in this kind of a material. If a material fails due to corrosion or fatigued due to corrosion, if the corrosion is enhancing, or let's say decreasing the fatigue life, we are going to call this as corrosion fatigue. Right, so let's come back to the question. So here they are describing the material as sound and smooth. Right, so we have a smooth specimen with us, meaning if we have a smooth specimen, so the surface roughness, this guy, meaning if the surface is smooth, it takes a longer duration of time for a crack to form. Right, so let us go on with the options now. Longer time in initiation than propagation, this looks good. Let us see all the other options as well. Longer time in propagation than initiation. They are claiming that the initiation time is going to be less, but this doesn't happen. Because of the smooth surface, it takes a longer duration of time to initiation. Equal time initiation is propagation, again this is wrong. No time in propagation, again this is also wrong. So the left out is option A. Option A is the correct answer. Right, so let me move to the next question here. uh, right, okay, stress curve is always a straight line for. Right, so if I draw a stress strain curve, we're going to have a straight line first, and then the material is going to yield, then we have a plastic region, and then we are going to have the ultimate point, and we are going to have the failure for a ductile material. Right, so in this we are going to have a point which is called a proportionality limit, and we are going to have another point wherein we call it as elastic limit, and then we are going to have the plastic region. In this region, without any increase in stress, the strain is going to increase. This region is non-linear region, and this is going to be the linear region. Right, so under this, the distance between this point and this point is usually very less, and it changes depending upon the material that we are going to use. Right, so coming back to the options now, they're claiming that it is an elastic material. Again, this is also for an elastic material. Again, we have a lot of these curves and all here. materials obeying the Hooke's law. Material which obeys the Hooke's laws will be under the proportionality limit, meaning what does the Hooke's law say? Hooke's law says the stress is going to be directly proportional to the strain under the elastic limit. So in the actual condition, the proportionality limit and the elastic limit is going to differ, is going to be very much small difference between those two. But in ideal cases, we are going to consider the proportionality limit as the elastic limit, right? So elastic plastic material. So if we are under the plastic material, it is no longer that the stress is not directly proportional to the strain, right? So we are going to have horizontal line and we are going to have some undulations and crests and troughs formed there, right? So anyway, the only thing that suits us is the options 2. We are going to go for this, right? So the next question here, the term nominal stress in a stress strain curve for mild steel implies. So first of all, what does this nominal stress mean? So first of all, we are going to have two kinds of stresses. So one is nominal, or this is also called as engineering stress. The other one is the true stress, or let's say the actual stress, right? So in this case, in the nominal case, we are going to consider the original cross-sectional area in the calculation, right? So in sigma will be equal to P divided by A naught, and in the actual cases, we are going to have consider the actual area, which will be continuously changing. This is going to be with respect to time. So in this case, sigma actual is going to be the load applied divided by the actual area at that particular instant of time at which we are going to calculate the stress. Right, so coming back to the question, the term nominal stress in a stress strain curve for a mild steel implies. So whenever we are talking about nominal stress or engineering stress, it is always the average stress, right? Obviously, this is not going to be the actual stress. This is not going to be the yield stress. Obviously, all these are false. The option A would be the right answer. Right, so moving on to the next question, we have consider the following statements. Right, the principle of superposition is applied to. So first of all, what is principle of superposition? So let's say if we have a material something like this, and I just divide this into, let's say, two different things, two different cross sections. Let's say if I assume this A1 of section 1 and section 2, if I tell A1 is equal to A2, and if I have the same material for both of them, and let's say if the applied load is something like this, if I have, let's say, 100 Newton here, and let's say if there is a load applied of 50 Newton here, I'm going to have another 50 Newton here, right? So let's say 50, let's say LHS loads on the left hand side should be equal to the loads on the RHS, meaning that 100 Newton would be equal to 50 plus 50. So this would be how, this is how we would solve the problem. We are going to use again the Hooke's law. Sigma would be equal to E into epsilon, right? So again I'm going to write P by A here, and I'm going to write E into delta L by L. So usually the problem would be given for delta L, so I'm going to write delta L would be equal to P by E into L by A, right? So if I apply these kind of formulas for this, I'm going to solve the problem. So let's say how do I exactly solve the problem? So I'm going to take the section A here. Section A is going to have, let's say, so which of these two loads are less? So obviously 50 Newton is the lesser one, so I'm going to take the 50 Newtons here, right? So do I have 50 here? Yes, I can split the 100 Newton into 50, and again the rest of the 50 Newton is still with me. So I'm going to solve for this delta L1, let's say, right? So I'm now going to consider the section 2. In the section 2, let's say, I'm going to have, so this is going to be, let's say, L1, and this is going to be L2. So for this, I'm going to consider the entire length L1 plus L2 for this. Now, so I've already expended the 50 Newtons here, so the remaining would be 50, and obviously the remaining here would be 50. So if I solve this, I'm going to have delta L2, and the total deformation of the material is going to be delta L1 plus delta L2. So this is how we are going to solve a problem on uh, principle of superposition, right? So where exactly are we going to apply for this, right? So we are going to apply for linear elastic bodies, yes. Body is subjected to small deformations, again, yes. So if the deformation is larger, the material is going to be under the plastic region, so there we are not going to apply the principle of superpositions, right? And which of these four statements are true? Obviously both 1 and 2 are correct, so option B is the right one. Let me just go to the last question of today's video. So strain at a point is, right? So this is quite tricky, not exactly, this is just the basics. So let me just define what exactly is a scalar and what exactly is vector and tensor, so on and so forth. So scalar has a unit, but it doesn't have any directions, right? So for example, mass. So mass of a body has, let's say, 5 kilos of mass, right? So this is a quantity, but this doesn't have any directions, which doesn't mean any sense. Let's say if you have mass in 5 kg in, let's say, x direction, it doesn't really make any sense. So it only has unit, no direction, right? So next we have a vector. A vector is something, it has both unit and a direction. The best example is, let's say, velocity. So meter per second is the unit, and we'll also have in what direction, let's say in n cap, whatever it is, right? Nextly, we are going to have something called as tensor. So tensor is something very vast. Let's say I can have a scalar tensor, or I can also have a vector, or I can have something which is quite different from all of this. I can also represent a quantity which doesn't have any unit, right, but it has a direction. So these kind of quantities can also be represented with the tensor, right? So usually tensors are represented by matrix, whether it might be 2 cross 2, 3 cross 3. Larger than this, higher ranking matrix can also be used for larger materials, but we're going to have even these quantities can be represented using a tensor, right? So strain is a quantity which doesn't have any unit, but it also has some direction, right? So material can be elongated in, let's say, x direction or y direction, in z direction, so on and so forth. So the quantity, or the, let's say, strain is represented by a tensor, right? The tensor would be the right answer. So hopefully this video has been helpful for you. Happy learning. I'll see you in the next video. Bye bye, take care.